chicken jockey. Wait, no, we're not doing that. We're here to do serious things. We're going to do some problems. We're going to practice alternating series types questions, interval of convergence types questions. And so we're going to get some practice with our root and ratio test. These are useful things to know. And so we're going to get good at them. Let's get to work. Determine whether the following alternating series converges or diverges. So we know this is going to have something to do with an alternating series because they were very clear about it. It's alternating series. Now, what does it mean to be an alternating series? What's alternating? Alternating means you're switching plus, minus, plus, minus. And in other words, you should expect you have something that looks like this. A minus 1 to the n in some way, shape, or form lurking around somewhere. Okay, so that's what we mean by alternating. Now, we need to figure out, does this converge or diverge? So there's two conditions. Namely, number one, does it alternate? And we're already told it alternates, but we can see there's that plus minus 1. Sometimes they'll do something sneaky, which is they'll make it look like an alternating series when it's really not an alternating series. So they'll have like 2 plus minus 1s that somehow cancels. So be careful. But now, the second thing is you say, look at the parts that's not the alternating part. Okay, now, does this decrease to 0? And that's our question. And in other words, if it goes down to 0, it alternates. If it doesn't go down to 0, I was going to say, if it goes down to 0, it converges. If it doesn't go to 0, it doesn't converge. Now, there's a technicality here. It's not just that it goes to 0. There is this notion of decreasing, which is to say that as n gets bigger, the terms get smaller. So it's really going downhill. And so we say, well, we just need to make an observation. Since 8 over square root log n, and the 8 doesn't really have any effect. But the key thing here is log n. Log n, the larger the value of n, the bigger this term is downstairs. So this is a decreasing function. And it goes to 0. Then the conclusion is the series converges. And notice that we are only asked about convergence. We're not asked to be, well, can you be a little bit more specific? It just says, hey, does it converge or not? And so for alternating series, it's rather a simple test. Are you decreasing to 0? Yes or no? And then if the answer is yes, convergence you will have. If the answer is no, it gets a little bit dicier. But we are good to go. We converge. Cool times. Good beans. What might happen? So one thing that could happen is when you have an alternating series, there's this test, and you say, hey, does this go to 0 or not? What would happen if it didn't go to 0? Let's just throw out a hypothetical. If it didn't go to 0, what's our conclusion? Our conclusion is diverges. Why? Well, because there's another test. And the other test is the nth term test. So if it doesn't go to 0, you have to diverge. If it does go to 0 and you're decreasing, it will converge. All right, there we go. One problem down. Let's keep going. Show whether the following alternating series converges absolutely, converges conditionally, or diverges. So there's sort of 3 paths that we can walk down. And so it's not just converging, it's like, what kind of converging are we talking about? Okay, so let's see what we have. Now, we know it's an alternating series. Partly we know it because they told us. Okay, that's pretty easy to see that if they tell it to us. But we also see it right there, that minus 1 to the n. And so we say, well, hey, there's this other part here, this 1 n to the 3 halves. Now this decreases to 0. And so we say, well, we alternate, we decrease to 0, so we converge by the alternating series test. All right, so that's good. And what does that give us? Well, it gives us that we know we're not we know we're not here. We've ruled out one possibility. But now we have to narrow it and say, well, hold on, absolute versus conditional. So, next step, we want to look at what we would call the sum 1 to infinity, the absolute value. Now, what does it mean? It means take out the alternating. In other words, get rid of the plus minus nature. Everything's positive now. So, all right, well, what's the plus minus part? It's this minus 1 to the n. So for us, we're saying, oh, so now look at this sum. And we ask the question, converge or diverge here. If the answer was converge, then we'd say it's absolutely convergent because there's this absolute. If the answer is diverge, it says, uh-oh, well, we needed the plus minus, so it's really conditioned on having that plus minus. So it's conditionally convergent. Okay, so let's look at our sum. What do we have? Well, this is a p series, right? 1 over n to a power. And so we say, aha, this is a p series. And we even are more specific with our value for p is 3/2. Now, it turns out 3/2 is bigger than 1. And so this converges. So what does that tell us? Well, it tells us we don't need the plus minus 1 to the n. Even if we throw that away, it still converges. So our conclusion is, so the original sum, minus 1 to the n, 1 over n to the 3/2, is absolutely convergent. Or it converges absolutely. However you want to say it. So there we go. I will say one of the things that you probably want to get the hang of as we get ready for our upcoming exam, and even for this quiz, practice like writing statements. This, so that. And, because of this, we get that. And so we're going to actually look for those kinds of statements and sentences. And I know you like sentences. What is this? English? I didn't sign up for an English class. But really what we want to see is we want to see thought processes. And so if you just write down, oh, absolutely convergent, you're like, well, yeah, that's the final answer, but that doesn't satisfy the show. So the show is, hey, can you justify all these intermediate steps along the way? So make sure we include that information as well. All right, good. Let's keep moving on along. Determine the minimum number of terms needed to estimate the sum of the convergent alternating series with an absolute error of less than 0.001. Now, there's a little bit of a caveat in the way this problem is phrased, because technically the way this problem is asked, we can't answer it without better tools. But there's a sort of an underlying, the way the problem was meant to be asked. So let's talk about what this problem is trying to ask us, just so we're clear. What we have is we have this sum, and it will converge, because it says, hey, it's a convergent alternating series. And we see alternating, and we look at these terms and like, oh yeah, you make bigger n, you get a smaller number, it goes to 0, it's decreasing, life is good, so it converges. It's very easy to see if we have a convergent alternating series. Okay, so there's some number. I'll call it L. Some people call it S. Now, we say, okay, what's our goal? Well, we want to say, how far do we have to go so that if we just stop at, say, the nth term of this series, and I'm just going to call this here, I'm just going to call this a sub n, just so we have it general. We want this to be less than or equal to 0.001. All right, that's our goal. That's our goal. Okay. So how do we get there? Well, because of the way the problem is stated, we'd have to know what is this, and we have to say, well, okay, start going through values of n, and when do we go below? But what we're trying to actually get at is to say, this alternating series has a beautiful built-in error bound. So here's what we really wanted to ask. Let me switch colors since we're saying this is what we're really after. If we go up to the nth term in the series, then what's true is that how far we are away is at most the next term. So if I stop at the nth term, it's the next term, an plus 1. Now, this is not a tight bound, and usually you'll have done much better, but we're not always after the best bound. We're after a good bound, and this is a good bound. So, in our case, we're trying to say, oh, really, I just want to make sure that this is small. That's the real goal. All right, well, what is this number, by the way? Well, if you count how many times you need to move the decimal place over to get to 1, you have to move it 1, 2, 3 times. So that's 1 over 10 cubed, or if you like, that's 1 over 1,000, whatever way you want to look at it. Okay, so that's our goal. So here is what the problem is secretly asking us. Solve for n, given that this is true. All right, now that we understand what the problem really wants us to do, we say, okay, well, this says what? Well, 1 over 7 times this n plus 1 quantity squared minus 5 needs to be less than or equal to 1 over 1,000. Well, flip both sides. And if you flip both sides, you'll flip the inequality. So that becomes 7 times n plus 1 squared minus 5 needs to be greater than or equal to 1,000. And okay, so that says n plus 1 squared times, well, we'll add 5, 1,005 over 7. And what is that? Okay, let's see if we can't get a quick estimate. Wow, this takes me back. All right, so we'll just do some very simple things. 1 subtract. This is not necessarily the most clever way to do this. 7 goes into 30. That's 4 times. That's 28. That leaves us with 25. So that's 143 point something. Okay, so we need n plus 1 squared greater than or equal to 143 point ... Okay. All right. Well, 143, that's a pretty good number, right? And for a square root, because that's really close to 144. So we say, oh, okay. Really, as long as n plus 1 is greater than or equal to 12, life is good. All right, so what do we do now? Well, we subtract 1, and that leads us to the conclusion n has to be at least 11, and there we go. So we know by the time we hit our 11th term, our error will be fairly small, smaller than this 1 over 1,000. And that's it. That's it. Now, I say that's it as if it was trivial, and it's not quite trivial. So the key here is if we're dealing with alternating series and we're trying to do something about error, just remember, go to the next term. The next term drives the error bound. Is it the best? No, but it's good. And it's the one that we use. So make the next term less than what you want, and then solve for n. And don't forget that there's n plus 1 because it's the next term. And so anyways, the answer is we need to go out to 11 terms. And that's it. Yay! Let's keep going. Find the function given by the power series, and there's this function, sum 1 to infinity, x minus 3 over 4 to the nth power when x is between negative 1 and 7. Now, we're not going to worry too much about this part right here. That's not going to be our main concern. We'll point something out when we get to the end and say, oh, isn't it interesting? But for right now, we say, okay, let's see what we have. And, well, what do we have? One of our nice basic facts is about geometric series. And we say this has a geometric flavor. So let's remind ourselves about that. So we have sum, k equals 0 to infinity, of something to the k power is equal to 1 over 1 minus something. And I'm stating it in this way. I know it seems like that's kind of a weird way to state it, Steve. Good. But what do we have here is we have a box. And we ask the age-old question, what's in the box? What's in the box? And another way to think of it is you have a mold. And like, okay, I got to fit the mold. And so when we're thinking about, hey, what can we do with things? It's like, well, we have some basic building blocks. We say, well, let's try to morph things so they fit the mold. And now we're like, oh, yeah, this feels like x minus 3 over 4 fits the mold. And then we'd be like, yeah, but there's a catch. And I don't know if you've seen it yet, but you might say, hold on, wait a second. Notice something about where we start our sums. This says start at 0. This says start at 1. And that changes it a little bit. Okay, so how do we fix that? Well, there's a couple of ways to think about it. So I want to talk about sort of two ways. Let's do two ways. One way is we could say, in general, we can do the following. If we have a geometric sum k equals 0 to infinity of a r to the k, it's a over 1 minus r. So what we really have is we have the following. We have a is first term. R is your multiplying factor. So what you multiply by at each stage. And so for us, we say, okay, so this is geometric. We just have to say, what's our first term? So the first term is you plug in n equals 1. So first term for us, so we have our sum, n equals 1 to infinity, x minus 3 over 4 to the n. So this is geometric. First term, x minus 3 over 4, over 1 minus, okay, now what's r? Well, it's x minus 3 over 4. All right. And this stage, multiply top and bottom by 4 over 4. And if we do that, we get x minus 3 on the top. And then downstairs, we'll get 4 subtract x minus 3. And that becomes x minus 3 over, and minus minus makes a plus, 7 subtract x. And there we go. Okay, now that's one way to handle it. Now, another way to handle it is to say, gosh, couldn't we just make it go from 0 to infinity? And we can. Okay, so here's the other way. And we say, well, I want this sum. But in order for me to use this rule, I have to get my sum to start at 1. And there's a couple ways. And like I said, I'm just going to show you one. So let's make it start at 1. Start at 1, start at 0. Let's make it start at 0. And so we're going to do it. Like, wow, look at us. We're a bunch of wild and crazy people. But we say, hey, we got to fix it. Because we know these aren't the same. Because they differ. They differ in that this has one extra piece. So we say, okay, so to make them the same, we say, well, what's that extra piece that we just added? Well, we added this x minus 3 over 4 to 0, which is 1. So now we just say, well, subtract 1, and lo and behold, these are the exact same. Say, okay, great. Sounds good to me. So what happens? Well, now I can use this rule. So this becomes 1 over 1 minus x minus 3 over 4. minus 1. Okay, so on the first term, I'll multiply by 4 over 4, similar to what happened here. But what we get is we get 4 upstairs, and then you get this 4 minus x minus 3, which is 7 minus x, minus 1. Okay, we'll now get a common denominator. So this is 4 over 7 minus x, subtract 7 minus x over 7 minus x. And what do we see? Well, we get upstairs, we'll have minus minus x makes plus x. 4 minus 7 is minus 3. And downstairs is our 7 minus x. So we still get the same answer because there's different ways to get there. Isn't that cool? We have different ways to get there. Now, I was going to make a comment. Here's the comment. We didn't really use this because it wasn't really a part of the answer. And where does this come from? Well, it comes from if you just say, hey, I have a geometric series, and we have convergence for a geometric series when our multiplying factor is x minus 3 over 4 is smaller than 1. Now, if you cross multiply, this says, oh, you mean that x minus 3 in absolute value is less than 4? Oh, this means that negative 4 is less than x minus 3 is less than positive 4. Oh, hey, that just means negative 1 less than x less than 7. So it was built into the cake in some sense. You know, it's not built in, baked into the cake. I got to work on my metaphors. So we didn't need it. But I did say I wanted to make a comment. Looking at these functions that we get as our final answer, do you notice any point that's a problem point? 7. Because if you look, you got to divide by 0. Isn't it interesting that, hey, that's also sort of limits how far we can go? What do you think? Is that a coincidence? I don't think it is. But, of course, that's a big story that's not for us to tell. But, what an interesting idea. All right, let's keep moving. Find the radius of convergence r of the series 3x to the power of 2n plus 8 over 3n plus 5. All right, so when we're after radius of convergence, and we know we're after radius of convergence, we say, hey, you know, we really just have to either use a root test or a ratio test. That's it. We always use root test or ratio test for radius of convergence. And we say, okay, well, which one are we going to go with here? Root versus ratio. And I think either can work. I'm going to go ahead and be a rebel. I'm going to go with ratio test here. And you might say, wait, I thought you were a root person. Aren't you an advocate who goes out there and says, you should always use the root test unless you see factorials, and then you use the ratio test? There's no factorial to be seen on this problem. So why am I going to go with the ratio test? Well, there's a little bit of an annoyance. This, in particular, this plus sign. I would find that annoying to justify with the root test, but with the ratio test, it won't be so bad. All right, so what's the idea? Well, the idea is to say, let's think of here our terms. We have these, we're going to call this our a sub n. And so we're going to take the limit as n goes to infinity of the absolute value an plus 1 over an. All right, so, well, let's start with an plus 1. And for that, just everywhere where we currently see an n, put an n plus 1. So we're going to have 3x to the 2, n plus 1 plus 8, over 3 times n plus 1 plus 5 times an. Well, divide by n, so I'm going to flip it. So I'm flipping the an, so 3n plus 5 over 3x to the power 2n plus 8. And because I want points, I know if I don't write this limit, they're going to take points off, so don't forget to write the limit. Okay, so what happens here? Well, a lot simplifies. Well, maybe not a lot, but some simplifies, and that's what we're after. We're after getting things to simplify. So notice here, we really have 2n plus 10 upstairs, and here there's 2n plus 8, and 3x to the power, 3x to the power, you subtract, say, hey, this really becomes the limit as n goes to infinity of this absolute value. We have 3x squared, 2n plus 10, subtract 2n plus 8. And then, well, we have this 3n plus 5 over 3n plus 8, right? Because I can just distribute the 3 through and just combine. All right, well, we look at this and we say, well, this becomes our limit as n goes to infinity. We'll just clean up just one more time. 9, 3 squared, absolute value of x squared, and then 3n plus 5 over 3n plus 8. Okay, well, what's the limit? Well, the 9 and the absolute value of x squared, freebies. There's no n. We know what they do. What about this part, this 3n plus 5 over 3n plus 8? Well, it's polynomial over polynomial. When you have polynomial over polynomial, you just say, are the degrees the same upstairs and downstairs? Oh, well, yeah, they are. Then say, okay, look at the coefficients of the highest powers and take the ratio. Well, so the highest powers are the n's. We say, okay, so take those coefficients and say, well, there's 3 and 3, right? Those coefficients, 3, 3. And, all right, divide. What do you get? We get 1. So you say, great, that's the answer, 1. Okay, so that's our limit. Now, when we're after radius of convergence, we take our ratio test. We say, make it less than 1. And now we need to start moving things around. So we're not there yet. We're not there yet, but we're really close. We're really close. So we say, hey, this is absolute value of x squared. Move this across, less than 1/9. Now, is this our answer? No. Be careful. Because what do you see there? An absolute value of x squared. Now, when you're looking for radius of convergence, what we're looking for is we say, hey, we should see something of the form absolute value of x minus a less than r. And a is your center, r is your radius. It has to look like this. The problem here is this square. There shouldn't be a square there. So how to get rid of the square? Square root. So, square root both sides, you get absolute value of x less than 1/3. And notice this is the same as absolute value of x minus 0 is less than 1/3. We say, so it's centered at 0. So center is at 0. Now, we don't need this, but we can point it out. And our radius is 1/3. And so there we go. Our radius of convergence for this series is 1/3. Woohoo! Nice! All right, well, let's keep moving forward. Find the radius of convergence of the series, sum from 1 to infinity, 1 plus 6 over n to the power n squared, x to 3n. All right, so we're back in the same game, right? We're after our radius of convergence. So we say, okay, we need to do either a root test or a ratio test. And we say, well, okay, which one are we going to go this time? And I will say, let's go root. Everything is to a nice power, and there's no pesky plus signs we have to worry about. There's no factorials in sight. And so this looks like a pretty good candidate. So here we go. We're going to think of this right here. This is our a sub n. So we're going to take our limit as n goes to infinity, absolute value of a sub n to the 1 over n power. So this is our limit. N goes to infinity, absolute value 1 plus 6 over n to the n squared x to the 3n to the 1 over n. Now, we can use properties of taking things to power. So in other words, if I taking the nth root of a product of two things, I can take them separately. So also note this is a positive thing, so the absolute values aren't needed. All right, so this is limit n goes to infinity. 1 plus 6 over n to the n squared to the 1 over n. And here, we push the absolute values in. This becomes absolute value of x to the 3n to the 1 over n. And, all right, now from here, we're almost ready to do some nice things. Multiply these things together, right? Because in general, if you have y to the power a to the power b, that's y to the a times b. So we have n squared to the 1 over n. This becomes our limit as n goes to infinity of 1 plus 6 over n to the nth power. And here, it's absolute value of x to the 3rd power. And now we're in good shape. Okay, so let's pause and say, well, hey, we don't need to worry about this. How do we handle this 1 plus 6 over n to the nth power? And so we start thinking to ourselves, what to do? And then we're like, oh, wait a second. There's this nice fact on the formula sheet. It says the limit as n goes to infinity, 1 plus t over n to the nth power is equal to e to the t. And we're like, that's a pretty good thought for us to have. So in this case, we have what? T equals 6. So this goes to e to the 6. So our limit is e to the 6, absolute value of x cubed. And remember, this needs to be less than 1, because our goal is this converges, and so our radius of convergence comes from this. Well, we can move things across, and we say, all right, hey, this is the same as absolute value of x cubed less than e to the 6 downstairs. And we don't want that cubed. We want to get rid of it. So what we'll do is we'll take the cubed root of both sides. Okay, so we're going to take both sides to the cubed root, 1/3 power. And again, we just go through and say, what does that tell us? It tells us absolute value of x is less than 1 over, and multiply these powers together again. 6 times a third gives 2. 1 over e squared, and this is the right form, right? Because this is like absolute value of x minus 0 is less than 1 over e squared. So we're like, aha, perfect. We're centered at 0, and our radius is 1 over e squared. So here's our radius. And that's all we were after. And so we're done. We did it. Huzzah! Woohoo! Yay us. Yay us. That was nice. Good job. All right. Let's keep going. Find the radius of convergence, r. Oh, I feel like a pirate. R. Gotta find r. Of the power series, sum 1 to infinity, n factorial squared, n to the n, x minus 7 to the n, 3n factorial. Okay. Cool. Well, what do we do? Again, we feel like a broken record after the last couple problems, but we're after our radius of convergence, so we say to ourselves, well, that says we have to do one of two things. We either have to do a root test or we have to do a ratio test. And we say, well, which one should we go with? All right, and at this point in time, there's not really a choice. You got to go with ratio. And that's because we haven't really talked about how n factorial grows. And if you knew a little bit more about how n factorial behaved, then we could say, oh, you can actually use the root test, but I'm not going to tell you because I don't want to distract you. But we actually do know a little bit. spoiler alert, e is involved. That won't surprise you. All right, so we know we're going with the ratio test and factorials. Great. So what do? Well, we're going to brace ourselves. We have a lot of stuff to write down. So this says we're going to take the limit as n goes to infinity of absolute value of an plus 1 over an. Okay, so everywhere where we currently see, and remember here, this part right here, this is what we call an. So everywhere where we see an n, we're going to replace it by an n plus 1. So we're going to have n plus 1 factorial squared, n plus 1 to the power n plus 1, and absolute value of x minus 7 to the n plus 1. Notice the only place where absolute value is needed is this x minus 7. Nothing else can be negative. Then downstairs, we have 3 times n plus 1. I'm going to go ahead and write this as 3n plus 3 factorial. Okay, so that's an plus 1 times the reciprocal of an. So we have our n factorial squared, our n to the n, our absolute value of x minus 7 to the n, and our 3n factorial. Okay, now we say cool. Good news is some things cancel really quickly, and namely this x minus 7 to the n, there's x minus 7 n plus 1, so we're left with just one of those, and that's not surprising. Now, what do we want? Well, we want to cancel the factorials, and this is where we say, let's take advantage of what we have going on. Namely, that we have a lot of terms with factorials, and we can make an n plus 1 factorial look a lot like an n factorial. So how do you do that? Well, if you think about what does n plus 1 factorial look like, well, it looks a lot like n plus 1, and that factorial just says start with the number and start multiplying, and don't stop until you get down to 1. Okay, that's n plus 1 factorial. But you say, well, wait a second. If I just take off the first term, then the rest of it looks like n factorial. So you say, it's like n plus 1 times n factorial. And here's the beautiful idea. What happened is, as I said, this n plus 1 factorial is a lot of things multiplied together. Let's just pull off the first term and leave the rest as a factorial. But I didn't have to stop at the first term. I could have pulled off a couple terms. And then after I pull off a couple terms, I say, and what's left is a factorial. And the reason I point this out is, hey, I have a 3n plus 3 factorial. So what can we do? Well, we start pulling off terms. I'll pull off a 3n plus 3. The next term, that's 3n plus 2. Next term, that's 3n plus 1. All right? I'm just pulling terms out. Boom, boom, boom. This is what the start of 3n plus 3 factorial looks like. Now, the next term is 3n, and I say, well, whoa, hold on. I have a 3n factorial. And I say, great. Now, just put the rest of it into the factorial. So I pulled off here 3 terms. And so in essence, you see that plus 3 pulled off 3 terms. Plus 1 pulled off 1 term. Now here, this n plus 1 to the n plus 1, I'm going to pull off 1 term. And that 1 term is just, I'm going to have a plus 1 there. Okay, so let's update where we're at. We have, this is the limit. As n goes to infinity, we have an n plus 1 times n factorial squared. Okay, so that's there. N plus 1 to the n times n plus 1. An absolute value of x minus 7. And a 3n factorial. Okay, that's upstairs. Downstairs, we have 3n plus 3, 3n plus 2, 3n plus 1, 3n factorial, and then we have n factorial squared and n to the n. All right. Well, some good news. We get more cancellation. And in particular, we can get the factorials to cancel, and life is good. That's why we like doing our ratio test when we see factorials, is so that we can get to this stage and say, hey, the factorials are canceling out. Now, what's left? Well, there's two, or maybe three, depending upon how you count. Let's worry about these pieces. They look kind of similar. N plus 1 to the power n, n to the power n. Let's put those together. And if we put those together, well, what we'll have is we'll have n plus 1 over n to the power n. Okay, so those are those two pieces. And then we have some polynomial stuff. We have this n plus 1 squared, this other n plus 1, then these polynomial pieces here. So let's put all those together. And so we actually, if you look, we have like an n plus 1 cubed over 3n plus 3, 3n plus 2, 3n plus 1. Okay? And finally, we have an x minus 7. Well, the good news is we're almost there. And you're probably like, oh, I don't know, it doesn't look very good. Hold on. Looks can be deceiving. The end is near, but in a good way, First off, this inside becomes 1 plus 1 over n to the n. Now, this is polynomial over polynomial. You check the degrees. Upstairs, degree 3. Downstairs, degree 3. Nice. And you say, we like that. So what are we going to do? Well, we can look at leading coefficients. We've done that before. And so this time I'm going to do something a little different. It says, divide out the growth. So imagine I'm going to pull an n out of each of these terms. So I have an n cubed times, because I pull an n out of each piece, 1 plus 1 over n cubed, over, here I have an n cubed, times 3 plus 3 over n, times 3 plus 2 over n, times 3 plus 1 over n. And the thing that happens here is the n cubes cancel. So we're essentially canceling the growth. I like to call it, we're applying the brakes. We're pushing on the brakes. Slow it down. Pump the brakes. And the key is to slow it down just enough so it's not heading off to infinity. It's not going to 0. It's going to numbers. We're getting it just right. And then our x minus 7. Okay, finally, we're in the home stretch. Here we go. 1 plus 1 over n to the nth power. It's on the formula sheet. E. These 1 over n's are going to go to 0. So we have a 1 cubed upstairs. And downstairs, 3 times 3 times 3, that's 27. And now this, well, it's always just absolute value of x minus 7. So what we get when we put it all together, we get e over 27 times absolute value of x minus 7. Now, in order to converge, we want this to be less than 1. So we're going to just move this across, and that tells us that absolute value of x minus 7 needs to be less than 27 over e. And we're in the right form. Absolute value of x minus a is less than 27 over e, which is our r. So this here, this is our answer. This is our r. And we're done. Now, you might say, well, wait a second. We didn't use something here. What didn't we use? This minus 7. It's been lurking ever since the beginning. It's been hanging around. Why didn't we use it? Well, because that doesn't have any effect on our radius of convergence. It affects the interval of convergence because it's telling you where the center is, but having a different center doesn't change the radius. And so it doesn't have an effect. I could have put 2, 5, 6, a million, wouldn't change R. So sometimes some parts don't matter, sometimes they do. But that's it for now, for this problem. But don't worry, we have more exciting problems coming soon. Consider the alternating series, sum 1 to infinity, minus 1 to the n, u sub n. And so we see it's alternating, at least we suspect, because that minus 1 to the n. Of course, you have to check u sub n. Well, where u sub n is 6n over n squared plus 49. Now, the nice thing is, if you look at it, plugging in 1 to infinity, you get positive numbers. That's great. Now, what do you want in an alternating series? Before we read the next part, let's just remind ourselves, hey, we love alternating series because you just have to say, do the terms decrease to 0? Now, clearly, in the long run, the bottom is bigger than the top, so this goes to 0. But we need it to be decreasing. So let's see what this says. Find the term at which the un values start decreasing. That is, find the smallest value of n for which un minus 1 is greater than un. Okay, so when do we start going downhill? Now, this sounds like a hard problem if we think of this as a discrete problem. But let's not think of it as a discrete problem. Let's put on our calculus hat. We say, hey, let's think of this as our f of n. And so we say, well, let's think about our function f of x, which is 6x over x squared plus 49. And now we have a function, and we know how to talk about increasing, decreasing. You say, if we see f prime positive, that means we're going up. And if we see f prime negative, that means we're going down. So we could say, all right, let's do a Calc 1 check. So we get to practice. Oh, quotient rule, my goodness. Wow, talk about a walk down memory lane. All right, so here we go. Take the derivative. We're going to have quotient rule, so it's the bottom, x squared plus 49, times the derivative of the top, 6, minus the top, 6x, times the derivative of the bottom, which is 2x, all over bottom term squared. All right, low d high minus high d low over low squared. All right, there we go. There we go. What can we do here? Well, we can certainly factor a 6 out on the top. Might as well do that. And then we have our x squared plus 49. And then we're going to subtract x times 2x is subtract 2x squared over x squared plus 49 quantity squared. And then we say, well, that makes it 49 minus x squared over x squared plus 49 squared. And 49 minus x squared, 49 is a square, so this is really 6 times 7 minus x and 7 plus x over x squared plus 49 squared. And so what are our critical points? Well, the denominator is never 0. Okay, great. Because you square plus a square. Upstairs, negative 7 and positive 7. And so if you draw a number line, say, well, you've got yourself negative 7 and you got yourself positive 7. We don't really care about what happens with negative values, so because n is positive. When you plug in 0, what do you see? Well, you get 6 times a positive over a positive. You see f prime is positive, which means we're going up. when you plug in something bigger than 7, say 8, 10, 100, doesn't really matter. We'll go with 8. Positive, negative, positive, positive, altogether makes a negative. So we're increasing, and then we are decreasing. Now, that's f as a continuous function, but when we think about fx versus fn, the main difference is what do we look at? Fx says we look at everything. Fn says we sample. And so if we're increasing, then we're increasing as we sample. If we're decreasing as we sample. And so now we're like, we know that this Fn, we are going to be fine as long as we're here in this region. So our punchline is we start decreasing from the 7th term. So U7. So U7 is going to be bigger than U8, bigger than U9, so forth and so on. So that's where we're starting our decreasing. It can be a little bit tricky to say, oh, n means this, n means that. But the key here is we start at U7. Now, if you look at it, before U7, we're going up. U1 is less than U2, is less than U3. U6 is less than U7. So U7 is when we peak. So it's after U7 that we start going down. Oh, yeah, this problem, it's going down. Oh, yeah. But there we go. Ha-ha, a little bit of calculus. Woohoo, quotient rule. Ha-ha, deja vu. Find the interval of convergence of the series, sum from 6 to infinity, 3n, x minus 4 to the n over n. Now, don't get distracted by the starts. They never matter. So if you see something that's not 0 or 1, don't be like, oh, what does that mean? It means nothing. It just means don't worry about it, because it's always the tail. What happens for big values? That's what matters. All right, so we're after interval. So we've done a lot of problems with the radius. This says we want you to go one step further, one more step along the way. And so, okay, so if we're after our interval of convergence, we have a two-step process ahead of us. We need to do step 1, which is the radius, and we have to do that by either root or ratio. And looking at this looks like a very simple thing, so let's go with the root test. And then step 2 is we need to figure out endpoints. What's going on at the end? Because essentially, the first step is going to give us everything but 2 points. And you say, well, but what about those 2 points? So you have to treat those very, very specially. All right, so let's begin with our step 1. So here we go. Step 1. We're after our radius. Now, the thing is, think of this as just the whole thing. This is your a sub n. When we're going to apply root or ratio, and we said here we're going to do root test. Sometimes you do ratio test. Honestly, if it asks you for an interval of convergence, 99% of the time it's going to be a root test. Because dealing with factorials is going to be tricky at endpoints. So if they're giving you something with endpoints, there's not really going to be a factorial involved. It's really hard to do that. So just to be honest with you, if you see an interval of convergence problem, you should think almost surely it's going to be a root test. Okay, so here we go. We're going to take our limit. N goes to infinity of absolute value an to the 1 over n. All right, so limit n goes to infinity of, and we're taking our absolute value 3n x minus 4 to the n over n to the 1 over n. Okay, so we're going to push the absolute value in. We're going to push nth root in. And we'll go ahead and just maybe add a few things that we probably would just do automatically. 3n to the 1 over n. We'll write this as 3 to the n to the 1 over n, almost always we skip this step and say, hey, that's a 3. But we'll write it down this time. The absolute value will come into play here because x minus 4 could be negative. We don't know, so we have to put that in absolute value. So to the n, to the 1 over n, and downstairs we have n to the 1 over n. And of course we say, hey, a power to a power, multiply the powers together. So this becomes the limit. N goes to infinity of 3. Similarly, x minus 4, n to the 1 over n, x minus 4, and then you have an n to the 1 over n. And at this point, you're like, how do we handle the downstairs? But this is where we have a great, like, oh, wait a second. There's a nice fact about limits. It's pretty good. It's so good, it's on the formula sheet. Limit as n goes to infinity, n to the 1 over n power is 1. So that tells us, hey, this part downstairs goes to 1, and that's the only thing that involves n. So life is good. Life is wonderful. We get the following. This becomes 3x minus 4. Okay, now, in order for this to converge, this needs to be less than 1. And, all right, well, we can move things around. That says x minus 4 is less than 1 over 3, which I write this as negative 1 over 3 is less than x minus 4 less than positive 1 over 3. So this just lets me drop absolute values. And, okay, so add 4. So we get 4 minus 1 over 3 less than x less than 4 plus 1 over 3. And if you think of 4 as 12 thirds, that says, okay, so you have 11 thirds less than x less than 13 thirds. Now, let's be careful here. This is not the full answer, but what it's saying is you have the following. You have your center is at 4. Then you go out both directions a distance of 1/3. That's this value here. That's your radius of convergence. And we have these 2 points. We have 11 over 3, and we have 13 over 3. And at this stage, because we haven't done part 2 yet, but we've done part 1, at this stage, we know we converge in here. So those are all good points. And we also know we diverge out here. So those are all bad points. Those are places where the series won't make sense. But we're left with 2 points. These 2 endpoints. And that's why we have our step 2. What happens when we plug in these endpoints? So let's plug those in. All right, so we'll start here at 11 thirds. So at 11 thirds, we have the sum from 6 to infinity. We have 3n 11 thirds minus 4 to the n over n. Now, 11 thirds minus 4, you can kind of go back and say, well, what does that look like? Well, it's negative 1/3. So it's negative 1/3 to the n times 3 to the n. And if you multiply those together, what you end up with is you end up with minus 1 to the n over n. Does this converge? Yes, because we're alternating. That plus minus, hey, alternating, that's a good thing. And this n is driving things down to 0. It's decreasing to 0. So converges. And we want to include a brief justification by alternating series test. So it's not just enough to say it converges, throw in a reason why. Make sure you include that justification. Okay, so what does that tell us? That says, hey, 11 thirds, you are in. Now you might be saying, well, wait, Steve. It converges, but it's not a really good convergence. It's like that conditional type convergence. I know. The question doesn't ask us, after interval of convergence, you don't have to worry conditional versus absolute. You just say converge or not. Now, true fact, in between the endpoints, it's always absolute. Endpoints may or may not be absolute. They could be conditional, absolute, divergent. So you have to check. But don't worry about conditional versus absolute if you're worrying about interval of convergence. That's a different problem. Okay, so that was at 11 thirds. Now let's plug in 13 thirds. Well, we get the sum from 6 to infinity, 3n, 13 thirds minus 4 to the n over n. And 13 thirds minus 4, that's 13 thirds minus 12 thirds, that's 1/3 to the n. 3 to the n times 1/3 to the n is 1. And so we get this sum, 0 to infinity, of 1 over n. What can we say? It diverges. Why does it diverge? Well, it diverges by being a harmonic series. We could also say it's the p-series, but the point here is we have a reason why it diverges. Now, I should mention this, and so let me shade it and say, aha, you're out. You might be, Steve, very suspicious that when you needed green, it was green, and when you needed red, it was red. Well, you get the hang of these after a while. But what I want to say is that when you're testing the endpoints, the root and ratio test should fail spectacularly. If when you're testing the endpoints, you say, oh wait, this looks like it'd be pretty easy to converge by a root test or a ratio test. Whoops! Mistakes were made. Step back and catch yourself. As the great philosophers would say, check yourself before you wreck yourself. All right, so finally we put this all together and we say, what's the interval of convergence? Well, we could say 11 thirds less than or equal to, because we include that endpoint, x less than 13 thirds. Now, some people prefer a different notation. That's okay. You could also say bracket 11 thirds, comma, 13 thirds, parenthesis. Means the same thing. It's the same interval, just different notation. Make sure you have a notation that you're comfortable with, and it's a notation that your grader will be able to identify. And your grader is a smart person. They have a degree in math, and they're able to know that both of these mean the same thing. And but there you go. Okay, quick recap, because this is an important problem. You know, when it comes to like exams, they love these problems. They love these problems. And so it's like, I know it's coming. I'm going to be prepared. So when you're doing the interval, find the radius, doing the root test, and really you'll find more than the radius. You're going to get essentially everything but 2 points. Doing the root test, occasionally a ratio test, but it's almost always root test. And so carry out the root test, rearrange, and get your interval other than your endpoints. Be careful when you get to this step. Moving things around, sometimes you have to take a root of a power. Just don't rush yourself, because that's an easy place to make mistakes, going from here to here. So take your time and double check your work. Once you have the 2 endpoints identified, now you go to phase 2. We should have written down 2, so here we go. We'll write down 2 here. Those are our endpoints, and plug in your endpoints. And also include explanations about why you're converging or diverging, because they're going to look for that. And put it all together. Life is good. And got to do the work. Got to do the work, because sometimes you include both, sometimes you include neither, sometimes you include one. Do the work. You can do it. You're wonderful. Keep being wonderful. Get all those points. Got to get them all. Got to get them all. All right, one more problem. Let's do it. Consider the series, sum from 1 to infinity, 4n factorial, 2a to the power n, 2n factorial quantity squared. Find the integer m so that the series converges when m is less than absolute value of a and diverges when absolute value of a is less than m. If this is feeling like a root test or a ratio test, it's because it is. Essentially, it's just saying, hey, throw the test at this one. And which test are we going to use? We see factorials, and we say, aha, that's got to be a ratio test. So this problem is just saying, hey, throw the ratio test, and let's see what sticks. All right, so we're going to have, this is our basic term. I'm going to call this the a sub n. So here we go. We're going to take our limit as n goes to infinity of absolute value an plus 1 over an. And we start by saying, all right, let's do an plus 1. And for this one, we say, well, everywhere where we see an n, we put a n plus 1. So 4 times n plus 1. So I'm going to do this. I'm going to go ahead. Last time we saw this, I just wrote 3n factorial. 3n plus 3 factorial. I'll do it 4 times n plus 1 just to emphasize what's going on. And then here we have 2a. Now, a could be negative. And remember, there is this absolute value here. So that's the absolute value will come into play here. So it's going to be 2 absolute value of a to the power n plus 1. And then times, well, 2n plus 1 factorial squared. Okay, there we go. There's an plus 1 absolute value. Times, all right, the reciprocal of an. So we're flipping things. And again, absolute value comes into play. The only thing it affects is that a. So 2 absolute value of a to the n, 2n factorial squared, 4n factorial. All right. Nice. So from here, we sort of prepare ourselves. Maybe do some shoulder exercises for all the writing we're about to do. Okay. All right. Good. All right. Now, we have to rewrite. This 4n plus 1, this is really a 4n plus 4 factorial. We want to get to the point where we can cancel with the 4n factorial. How are we going to get there? We're going to keep pulling off the terms until we're down to 4n. Whoops, I pulled too hard. All right, so we have a limit. N goes to infinity. Start at the beginning, 4n plus 4. Keep pulling off terms, 4n plus 3. Keep going, 4n plus 2. You can do it, 4n plus 1. Almost there, 4n. Like, whoa, wait, hold on. 4n factorial. Stop pulling off terms. Everything else goes into the factorial. Okay, so that takes care of that. Here, I'll write this as 2 to the n, absolute value of a to the n. Okay, that's that part. And then here, it's our 2n factorial squared. Downstairs. Okay, here, well, I can write this as 2 absolute value of a, and then I can say, well, I also have 2 to the n, absolute value of a to the n, just to sort of prep myself. Now, this is, here we have really a 2n plus 2 factorial, so we're going to do the same thing. Pull off some terms. So here we go. Start with 2n plus 2. All right, we say keep pulling. 2n plus 1. Almost there. 2n. We're like, stop. So we stop and we say everything else goes into the factorial. So we pulled off 2 terms. Right? 4n plus 4. 4 terms. 2n plus 2. 2 terms. And that's being squared. Okay? And then we have this 4n factorial. All right. Well, now, if we pull things off, and we've done it correctly, we get cancellation, like those 4n factorials and these 2n factorials that are both being squared. Cool. The 2 to the n. Absolute value a to the n. Nice. And we look around and we say, well, there's not a lot left, is there? And what do you see? Well, we see a couple polynomial terms upstairs. a 2 absolute value A and a couple polynomial terms downstairs squared. Don't forget that. Let's talk about our polynomial terms. We have 1, 2, 3, 4 upstairs, so it's like a 4th degree polynomial upstairs. And then we have 2, but that's squared. So it's a 4th degree downstairs. Ooh, nice. So here's an idea. So everything upstairs is like a 4th degree top polynomial. Downstairs is like a 4th degree polynomial. And so in some sense, like, well, what's your leading coefficient? So what we can do is we can pull out the end of the 4th. And we'll just pull it out of the individual terms. So if we do that, what do we have? And I'm going to swap colors because I just have this impulsive urge to swap colors a lot. What can I say? I don't think it's a bad thing. I like colors. All right, so I'm going to pull an n out of each one of these 4 terms. So I have 4 n's. N to the 4th. Then I'll have 4 plus 4 over n. 4 plus 3 over n. 4 plus 2 over n. And 4 plus 1 over n. Downstairs, well, I'm going to pull an n out. But remember, it's being squared, and n out here. That's being squared. So I still have n to the 4th. Still have the 2, the absolute value of a. And then we have this 2 plus 2 over n. And that's being squared. And a 2 plus 1 over n, and that's being squared. We can again cancel the n to the 4th. This is the reason we're pulling it out is to say, hey, let's pump our brakes. Let's slow things down. Slow things down so that we can have our nice, soft landing and we get a number. That's what we want. We don't want things to blow up. We don't want things to go to 0. Just right. Just right. That's our goal. All right. So we have limit n goes to infinity. Whoop. No. We don't need the limit anymore. Why? We were actually ready to go. Because what do you see? This 4 over n goes to 0, 3 over n goes to 0, 2 over n goes to 0, 1 over n goes to 0, 1 over n goes to 0, 2 over n goes to 0. All those parts go to 0. So what's left? We have 4 times 4 times 4 times 4 divided by 2 times absolute value of a times 2 squared times 2 squared. Well, okay, the 2 squared goes into 4, 2 squared goes into 4. So we can do that again. So we have 8 over absolute value of a. Ha-ha! Or perhaps, huzzah! Ha-ha! All right, so we have made progress. Beautiful progress, actually. Okay, now, what's true? Well, this will converge when we are less than 1. And so now rearrange, you multiply the absolute value of a through. So we converge when absolute value of a is greater than 8. But same argument, we diverge when this is greater than 1. So we're going to diverge when absolute value of a is less than 8. So what's our integer m? Well, our integer m is 8. So that's what we're after. So as long as the size of a is bigger than 8, then the sum converges. And there we go. All right, we finished. We made it to the end. Good job, us. Good job, us. Woohoo! Well, thank you for working so hard. And I think this is the last official quiz, right? It's so sad to see things come to an end. But don't worry, we always have that test to look forward to. Thanks for joining me. Thanks for putting in the work. You can do this. You're wonderful. You're wonderful. I believe in you. I hope you do great things. All right. Take care. Bye.